This is an illustration of free settling, where the bigger particles settle faster than the smaller ones. The red's the biggest, the blue's intermediate, and the yellow's the smallest. And basically they're settling without any interference with each other, which is why we say free settling. Happens at low concentrations. If we move up above a concentration of about 1% by weight, then we move into hindered settling, and you can see now we have the red, the yellow and the blue particles again, but they're not settling like they were with free settling. They're settling what's called en masse. They're settling under what's called hindered settling. And if we were to trace the interface, that's the boundary between the settling solids and the completely clear liquid called the supernatant that's left behind, then that interface plotted against time looks like the graph on the right. It's a straight line and then reaches a period where it starts to curve over a little bit and eventually becomes flat when everything's settled out. So that's hindered settling, and that's the classic height against time plot, and it's the plot of the interface during hindered settling. We can get a lot of information from that plot by careful analysis. And this is the illustration of the zones that occur. There's the interface plot on the left hand side now, and if we take a fixed point in time, the zones are shown on the right. There's the supernatant, the clear liquid, the original concentration zone, variable concentration zone, and then sediment at the bottom, and that's at a position, fixed position in time, t. And here is some sedimentation. This is a fairly fast sedimentation. It's normally a much slower process than this, and typically performed in batch jars like this, measuring cylinders like this. The good news from the design point of view is that the sedimentation rate is not dependent on the vessel area. So laboratory tests using measuring cylinders are very good for designing industrial thickeners much bigger. That's industrial devices much bigger in area for separations. And you can see there was an interface, and if we zoom in a little bit we can probably see that interface a little bit better. There's no, here we go, there's another shaking up and settling, and you can see the interface quite clearly now. The supernatant liquid is not completely clear, but it's not bad. There's just a very few solids left there. And if we were to plot this against time, we would see that it had a straight line and eventually a curve, and then when it was fully settled it would just become a plateau. And this is an unusually fast sedimenting system. Most things settle much slower than this. Sedimentation is very much light because it's cheap, it's gravity driven, so the energy requirements are very minimal. And you can see that the interface is now just coming below the gradations on the measuring cylinder, and it's pretty much going to finish somewhere around there. So that was a very high concentration. If we had that much lower concentration, it would have settled much faster. Here we have a more realistic system. This is gypsum, which is flue gas desulfurization gypsum from power stations. 5 measuring cylinders at different concentrations. In fact, the lowest concentrations on the left, the highest concentrations on the right. And we're not going to wait for those to settle. Here they have settled, and you can see that this isn't fully settled. This is at the same period in time, and on the left we've got quite a low sediment, and on the right we've got quite a high sediment. They're still settling, and if we zoom in a little bit, you'll certainly be able to see the clarity of the supernatant. Again, it's not crystal clear, but it's not bad at the higher concentrations. That's the highest concentration on the right, and then those 3 there are reasonable concentrations, and the 2 lowest concentrations on the left, you can see clearly that again the supernatant is not bad, but it's a little bit cloudy.